Collaborative work often requires the shared use of physical resources in addition to the sharing of information. While computers have made collaboration over documents and data dramatically more efficient, physical interactions remain largely unaided by computation. The goal of this project is to develop technologies and interaction techniques to assist shared users of physical objects. This storage area at the MIT Media Lab is shared by over a dozen people. About 100 identical plastic containers in the area hold a variety of supplies and materials for prototyping. Although the containers are labeled, users often add or remove boxes or change their positions, making locating any particular item difficult. This problem inspired the development of simple electronic labels that could make the past use of these containers visible. We named this prototype system TouchCounters, as these labels are analogous to the hit counters that record the past use of web pages. TouchCounters are electronic devices with bright displays and sensors for magnetism, acceleration, and infrared commands. Each label has an ID chip that identifies it uniquely to a network. The label is attached to the storage containers by a set of magnetic snap connectors on the reverse sides. Likewise, the containers attach to docking ports located along the shelving surfaces in the area. Once a box is set upon the shelf, it is recognized by an embedded web server that tracks its use. By default, the label on each box shows a green pattern that indicates its recent frequency of use. The more times the box is taken off of the shelf, the more pixels are illuminated upon the display. When the entire set of containers is viewed from across the room, the aggregated independent displays comprise a spatial map of usage frequency. Thus, the most popular items can be used as starting points in a search. In addition, the boxes can be physically sorted such that the most commonly used items are easy to reach. Once a container is removed from the shelf, users can see how its past usage correlates with that of other containers. The orange pixels indicate how many times boxes have been used concurrently in the past. After a few seconds, the system returns to its default state. This information allows users to rapidly locate a group of boxes that might be used to accomplish a given task. In addition to the interface for automated display of box data, we have implemented a mechanism for explicit annotation of the containers. By pointing an infrared remote control at the boxes, users can attach simple graphics to the labels. These graphics can reflect common attributes such as ownership or the stage of assembly of their contents. One convenient aspect of using infrared technology is that users can rapidly drag a common label across multiple boxes in physical space. Finally, because all usage data is tracked by a centralized web server, the state of this system can be viewed on a web page. Here, a user removes a box from the shelf. We can see the web page update to reflect the missing container. When the box is replaced, the server increments its usage count. This feature could eventually be used to automate online ordering or restocking of materials. In closing, we have designed a lightweight information access system to support collaborative physical work. Our future work will examine how graphical interaction techniques like parametric queries and direct manipulation can be employed for interacting with physical world objects. We hope that this work will enable the natural and seamless interfacing of physical environments with information systems.